Good morning, good afternoon. My name is Jose Carrillo.
Elisa Aguilar, Elizabeth Quinonez.
And Andy Topete.
Today we will be speaking about our senior project, which pertains to UAV-assisted 5G wireless networks with quality of service constraints. In this presentation, we'll go over a general overview of what encompasses our project, problems to solve, the project objective, CPLEX, its formulation, the process, our proposed solution, Bender's decomposition, and the outputs. Our project uses a master optimization formula that places UAVs in an optimal location in order to provide the user's quality of service when a ground-based station is down. These techniques are implemented in IBM CPLEX to show us the locations and other variables important to our network. In our results, we see how the master optimization formula provides a few errors because of the non-linear constraints. Because of this, the Bender's decomposition strategically must be implemented in order to run our simulation. The main issues that the project tackles are proposed in a series of questions. How do you provide service to users when there is a failed tower? How do we continue to service users if there is poor network coverage? And lastly, how long would it take to fix these issues? The main project objective is to minimize the number of UAVs to provide the user's quality of service when one or multiple ground-based stations are down. In order to tackle these issues, we use CPLEX, which was an optimizer which provides flexibility, high-performance mathematical programming, solvers for linear programming, mixed integer programming, quadratic programming, and quadratically constrained programming problems. These solvers include a distributed parallel algorithm for mixed integer programming to leverage multiple computers to solve difficult problems.
So next we will be going over different variables and constraints that we need to consider during our formulation. So first we have our binary variables. The first variable we have is SIJ of K, which helps us determine whether the UAV I is active at location J. So if the UAV is active at a specific location, we will be seeing an output of 1, otherwise 0. The second variable is SIJ0. This determines whether the UAV I is in standby mode at that specific location. So same as the active UAV, if the UAV is in standby mode, it will output a 1 or else a 0. The last variable would be ULMI of K, which determines if the user L receives a physical resource block, PRBM, from UAV I when a GBS is failing. And then in our formulation, we have two continuous variables. So PLMI of K determines the transmission power from the UAV to the user on the PRB when a GBS is failing. And our FI of K is determining the flying time of the UAV to the served GBS. So here we broke down the different constraints that we used in our formulation. So our constraint B is ensuring that a single user can only use a single UAV. Constraint C, the total energy consumed by UAV I from transportation to and from locations, as well as transmission energy, does not exceed the total battery capacity. Constraint D, the total flying time by UAV I to the service location to service a failed GBS is captured. In constraint E, at most, a single PRB at UAV is being used by one user. In constraint F, UAV is used if at least one user is using it. In G, UAV is not being used if no users are using it. So this will be the inverse of our prior constraint. In our H constraint, the UAV can be used at one location only. This accounts for the possibility of the UAV not being used at all. In constraint I, UAV can be used for failure mitigation only if it is available in standby mode. In J, deployment of the UAV does not exceed the maximum latency requirements. In constraint K, the UAV is not transmitting if it's in standby mode. Constraint L, the transmission power can only be a non-zero value if the UAV is serving a user. And in constraint M, the power consumption of the UAV is limited by the maximum power budget, or Pmax.
Now, in order to get the optimal network, we must go ahead and incorporate all of our previously mentioned constraints into the master problem. These constraints will be crucial in maximizing the potential of our network. In the master problem, first we're going to have the problem to solve for the minimum number of UAVs that the network will require. We wouldn't want extra UAV resources sitting around if they won't actually be needed. This will also minimize the cost of implementing the system. Second, the problem will also solve for the most optimal location for each of the given UAVs. Each of the locations available has a specification to it. This parameter can either be categorized as a 0, that being a landing location, or a 1, stating otherwise. Within our solution, we allow the program to also pick the best solution, whether it be a landing or otherwise. But in the future, if there are specific demands, the changes can be made accordingly. This would accommodate for the specifications of each available location. The master problem had some difficulties, as the program cannot natively multiply a binary variable by another binary variable. Our constraint D is a non-linear constraint and had to be linearized. Therefore, we had to split the constraint into a whole new formulation, one that wouldn't require the product of two binary variables. The master problem was giving us results not consistent with our constraints or our parameters. As we can see from the results in the top right corner, it states that there are 4 active UAVs at location 4. However, this is not possible, as there are specific restrictions set to 1 UAV per ground base station.
So in order to fix these problems, we are going to use a technique called Bender's decomposition. Bender's decomposition is when the variables of the original problem are divided into 2 subsets, so that a first stage master problem is solved over the first set of variables, and the values for the second set of variables are determined in a second stage subproblem for the given first stage solution. So for this process, we have 2 different mod files within our Cplex code. In the first mod file, we have our master problem. Here, the binary variables are fixed to 1s and are solved for the continuous variables. This means that the constraints involving just the binary variables are not included in these constraints. In the second mod file, we have our secondary problem. In this problem, we have our continuous variables fixed to integers that are taken from the solutions of the first problem. It is also noted here that the constraints involving only continuous variables are not included in this mod file. When running both the master problem and the secondary problem, we get the correct output data corresponding to all ground base stations up and running. With the master problem, it gives us the flying times and a transmission power of all zeros, which means that the UAV is not supporting any users. In the secondary problem, it gives us the correct standby, active, and PRB distribution indications. And now we'll be demonstrating our code.
So after taking the whole problem into account and implementing all of the constraints within the master problem, we determined our parameters. Within these predetermined parameters, we settled on a number of users, a number of ground base stations, and a number of UAVs, along with a few other parameters to attain a better overall solution. We set the number of users at a lone number, that being 4, to more accurately understand the behavior of our network. This number, however, can later be incremented to better accommodate for larger networks. And below, we determined all of our arrays and variables required to go along with our parameters. And now we can go ahead and run it. Takes a little time. You can see the timer right below. Actually, can't see the timer. Oh, okay. So here are the values that the program calculated. So we have our parameters right above certain values that we inputted manually, but what we care about are the decision variables. The capital F stands for landing or hovering locations. 1 being a landing location and 0 being a hovering. Lowercase f determines the flying time of each UAV, while P indicates the transmission power in watts, which is why the number seems so low. But as you could see in the S, there are no active UAVs except at this single location. Therefore, our S0 should have 1s to complement our S array, meaning these results are not accurate.
In order to fix the issues with the main problem, as previously mentioned, we are going to use the technique called Bender's decomposition. This means that we have 2 different mod files, the master problem and the secondary problem. Here you can see our master problem. We fixed our binary variables to 1. These are matrices of 1s that are gathered as seen here from our data sheet. It is important also to note that this problem still has the same parameter values as the master problem. Below, you can see the constraints that we used for this first master problem. It is important to note that we got rid of the constraints that only include binary variables. When you run the code, this problem, it solves for the decision continuous variables F and P. F is the flying time it takes for the UAV to get to the ground base station. Here it shows 5.36 seconds. The power shows the power the user is getting from the UAV. As we can see here, the power values are all 0, which is consistent with no UAVs. After, we take these values and use them for our secondary problem. As you can see here, we are still using the same parameter values. Now, however, our Boolean variables are not set, and the continuous variables are set to the values we found previously. It is also important to note that the constraints here are constraints that don't include only continuous variables. When running the secondary problem, you can see that it determines that with all ground base stations up and running, there are no active UAVs and all of the UAVs are inactive. This means that no users are getting a PRB from the UAV, which is consistent with having a properly running network. Lastly, in order to see all of our variables, we used our datasheet to export these variables into an Excel sheet to read. This concludes our senior project.
Thank you.